Hey everyone, and welcome to this explainer. Today, we're going to unpack the exact mental model that separates junior coders from highly paid senior engineers. Look, if you've ever felt completely overwhelmed trying to understand how these massive tech platforms are built, or maybe you hit a brick wall when you're asked to design a scalable application from scratch, well, you are definitely in the right place. We're going to take a deep dive into the foundational architecture principles that will frankly completely change how you look at system design. Let's get into it. We're kicking things off with a really powerful quote from our source material that perfectly captures the core problem here. It says, "The gap between a junior engineer and a highly paid senior developer isn't years of experience, it's how you think about systems." You see, memorizing a giant list of technical buzzwords is a classic junior mistake. Sure, it might help you pass a basic vocabulary test, but the second you have to reason through a brand new complex problem, you're gonna freeze. Senior engineers get those top-tier offers because they actually know how to reason about architecture, not just write lines of code. So here's our roadmap for the explainer. We've got 5 core pillars today. Number 1, the senior engineer mindset. 2, scaling, state, and caching. 3, managing distributed network failures. 4, decoupling with message queues. And finally, 5, databases and API contracts. Starting right off with Section 1, the senior engineer mindset. Okay, the biggest takeaway here is this: stop building a glossary. Seriously, true confidence in design comes from understanding the underlying principles that tie everything together, not just reciting the dictionary definition of DNS or a CDN. You need to start building a mental model based on the why, and more importantly, the architectural trade-offs. If you just collect flashcards of terms, you're literally just building a glossary, and that is not going to help you in a real-world scenario. Once you understand why a certain technology was chosen over another one, you'll stop blanking when you're put on the spot. Moving right along to Section 2, scaling, state, and caching. You hear it all the time, right? The solution to scaling is to just scale horizontally. Basically, just throw more servers at the problem. But here's the catch. You can only safely add more servers if those servers are acting completely stateless. Statelessness means the server doesn't remember a single thing about a previous request. Every single time a request comes in, it carries absolutely everything the server needs to process it, usually through a token on the client side. The server treats every single request like it's meeting you for the very first time. And this brings us to a massive trap. If your server stores session data locally, say a user's in-progress shopping cart, that user is now chained to that one specific server. It's kind of like having a favorite barista who is literally the only person allowed to make your coffee. If they call in sick, well, you're out of luck. This is called a sticky session, and it's a huge junior trap. Your load balancer's hands are tied, and if that server dies, the user's session goes down with it. Compare that to the senior approach, shared state. By offloading that state to a shared store, like Redis or a distributed cache, suddenly every server is identical. Your load balancer can route traffic anywhere, you can spin servers up and down dynamically, and you actually get real fault tolerance. So once your state is fixed, we gotta talk about speed, and that means caching. Now, caching is everywhere. Browsers, CDNs, app servers, databases. It can honestly feel like a dozen different concepts to learn. But actually, scratch that. Just stop memorizing different caches and ask yourself 2 basic questions. Where is the bottleneck, and how stale can the data be? That's it. Every single cache makes this exact same core trade-off. You are always trading speed in exchange for data freshness. You store a copy of the data closer to where it's needed, and you just accept that the copy might be slightly out of date. Once you wrap your head around that trade-off, you just need to know the 3 main layers. First, we've got CDNs. These serve static content geographically close to your users. Next, application-level caches, like Redis. These sit right in front of your database and are absolute lifesavers for read-heavy queries where you need millisecond latency. And finally, database query caches, which live inside the database itself. Understand these 3 layers, throw in a few concepts like time to live, write-throughs, and write-backs, and honestly, you'll easily handle the vast majority of caching questions. All right, Section 3, managing distributed network failures. We have to face a harsh reality here, and it's a concept people get wrong all the time when talking about the CAP theorem. People think you get to just pick 2 out of 3, consistency, availability, or partition tolerance. But listen, partition tolerance is not a choice. It is a mandatory constraint. In any real-world distributed system running over a network, partitions are going to happen. Nodes will lose connectivity, packets will drop. It's literally just a given. Because network failures are an absolute guarantee, What's really interesting is that this is the actual choice you have to make when the network drops. Consistency versus availability. Consistency means every single read gets the most recent write. If I update my profile picture, anyone who loads my page right after sees the new picture. Availability, on the other hand, means the system always responds to the user even if it has to hand over slightly stale data to do it. Now, the secret here is that you don't have to make this a global choice for your entire app. Think about Google. For them, strong consistency is completely non-negotiable for things like financial transactions, billing, and access control. But for a YouTube content feed, eventual consistency is totally fine. So please, don't just blindly say you're going to use eventual consistency for everything. Show you're thinking like a senior engineer by specifying exactly which operations need strict guarantees, which ones can be relaxed, and why. That brings us to Section 4, decoupling with message queues. Imagine a user places an order on your site. In a fully synchronous world, this is a very rigid chain. Place order calls check inventory, which calls process payment, which calls send notification. And all of this has to happen in real time before the user even gets a loading screen to go away. Do you see the huge risk there? You've built a Brill chain of dependencies. If just the email notification service gets a little slow or crashes, the entire order flow fails. Your system is only as reliable as its weakest link. And that right there is exactly why we use message queues. They break those rigid dependencies entirely. Instead of calling the next service directly, your service just publishes an event, like, hey, an order got placed, to a queue system, something like Kafka or SQS. Then the downstream services just pick it up and process it on their own time. By sticking a queue in the middle, your services become completely resilient to each other's failures. So if the notification server goes up in flames, no problem. The message just waits in the queue, the payment still processes, the user gets their confirmation on screen, and the email just sends whenever the notification service wakes back up. Finally, let's explore our last pillar, Section 5, databases and API contracts. Okay, we've got to talk about the whole SQL versus no SQL debate. People always frame this as old versus new, but that is completely missing the point. It is 100% about what guarantees your specific workload needs. SQL databases give you strict guarantees. They are safe for things like financial data, where a partial write would be a total catastrophe. No SQL, on the flip side, trades away some of those strict schemas and consistency rules so it can easily scale horizontally across tons of machines. That trade-off is actually a feature. It's absolutely perfect for massive user activity feeds or real-time analytics where slightly stale data is fine and you just need scale. Now, if you are going to use SQL, knowing the actual definitions of these ACID properties is just non-negotiable. Let's rattle through them. Atomicity means a transaction is all or nothing. If you transfer money, both the debit and the credit have to succeed, or neither of them does. Consistency means the database strictly follows its own rules, only moving from one valid schema state to another. Isolation means that if two users hit the database at the exact same millisecond, their transactions won't trip over each other. And durability means once a transaction is committed, it is saved to disk for good, even if the server unplugs a second later. So, how do we let the outside world actually talk to this beautiful system we've built? APIs. Your API is a strict contract, and changing it later isn't just tweaking some code, it's a massive, coordinated headache. You generally look at REST or GraphQL, and they optimize for different things. REST is simple, it's cacheable, and it's fantastic for stable public interfaces. GraphQL is super flexible. It lets the client request exactly the data they need, no more, no less. That's a total game changer if you have both a web app and a mobile app hitting the exact same backend, but needing totally different data shapes. But look, regardless of whether you choose REST or GraphQL, following a few universal rules of API design is going to save your team so much pain. You've got to be explicit about versioning from day one. Always design your endpoints around the resources themselves, not your internal backend logic. And please, document your contracts before someone downstream is forced to reverse engineer them. You really have to treat your API like an unbreakable promise to the developers using it. I want to leave you all with a bit of a provocative challenge today. Take these mental models we just walked through and try to apply them to the apps you use every single day. Like, how exactly do you think Spotify uses caching across its CDNs in your local phone storage so that a song plays instantly? Or when you use Venmo, at what exact millisecond does the system absolutely demand strong consistency, and when can it relax? Start asking why every time you open an app on your phone. You do that, and you'll be thinking like a senior engineer in no time. Thanks so much for joining me on this explainer, and keep building.